This is Lab 2 for Physics 1, dealing with projectile motion. The purpose of this lab is to observe an object moving in both the x and y directions at once. The primary physics principles will be using the velocity update to track how the velocity changes due to the forces acting upon the object, and the position update using the updated velocity to then track how the position changes. For calculating the forces, we have two forces, the force of gravity and the force of drag, given by the inverse of a drag coefficient multiplied by the speed squared times the direction of velocity. And the goal, what we're looking to hopefully find, is a graph that somewhat looks similar to what we have on the bottom right here, where when you plot y against x, you have this arcing motion. For the observation, my team threw a crumpled up paper ball. The paper ball is the system, and the Earth, everything else is the surroundings. Earth has gravity affecting the paper ball, and the air, the atmosphere of Earth, applies drag to the paper ball. For the computational model, I took the initial position and initial velocity from Tracker, then simply filled in the equations for the force of gravity and the force of drag. You add them together to then get the net force, and then fill in the velocity and position update formulas. For B, that required just messing around a bit to find a value that fit what Tracker showed. And then on the right over here we have showing how the velocity in the x and y directions changed over time, as well as that trajectory motion that is what we were looking for. And the top right shows what the model actually gave. Comparison between the two computational models, the one without drag being the top line, the one with drag being the very bottom line, and our observation being the middle line with only a few dots. The primary difference here is that the two computational models did not travel as far in the x direction as the observation, which one would expect that the no drag model would travel further in the x direction due to the lack of having any drag slowing it down in the x direction. However, if you want to scroll back to when I was showing the Tracker screen, Tracker actually shows that the ball is speeding up in the x direction. And initially I was very confused as to why this is, but the reason is that when I positioned my axes, they were slightly tilted, so that gravity was now influencing the ball in an x component, therefore speeding it up. And that would be why the computational models are slightly off from the observation. However, besides that, the no drag model adheres to the expected result of it not reaching as low of a point in the y-axis due to the fact that there is no drag slowing it down. Therefore, it maintains a positive y velocity for a greater period of time. And the no drag model, or the drag model, was then manipulated to have a b value that as closely as possible would replicate the observation. Now in this case, I purely went off of the final y position, which as you can see is very close. However, due to the fact that in the observation the axes are tilted and it is speeding up in the x direction to that, they cannot truly be the same in this comparison. Now the discussion. Well, what if the object were thrown straight up with the same speed, it would actually take longer for the object to reach the ground. If it were thrown straight up with the same y component of the standard velocity, then it would take the same amount of time, as the y component of the velocity is what dictates how long it takes for the object to travel up and back down again. However, with all of the speed now being put directly into the y component, that y component is now greater than it was before. What does it mean? Well, the computational model, neither of them represent the object reaching terminal velocity. However, what that would show is if the y velocity graph leveled out and stuck to one value, which if you scroll back a bit, you can see that it's starting to do so, however, it's not long enough. But instead, what you could do is simply just model it for a bit longer, and then it will reach that terminal velocity speed. Thank you.